Alright, so I'm going to do a few examples, or maybe two examples, of Chapter 5 type questions. Now remember, Chapter 5 is about discrete probability distributions. So if you were in class, you noticed that we did first a general discrete probability distribution, but then we did this thing called a binomial distribution. So let's do one example of each. Now the first example was when we just when we used a tree diagram to figure out the probabilities of different events happening. For instance, in this example here we say 36% of college graduates say they would change their major if they started college over again. This is from a Gallup poll just this year. Suppose we ask two random college grads about this issue. Let X equal the number of graduates who would change their majors. So we're asking two people whether or not they would change their major if they went back to school, if they started over again, and they can either say, yes, I would change my major, or no, they wouldn't. And we want to figure out, what's the probability of, one of them wanting to change their major, both, zero, that situation. So we start to make a distribution. So let's see here. We make a little chart here. Remember, our distribution is essentially just a t-chart where we have the outcome, we call that x, and p of x is the probability. Okay? So what are the options? Okay, well, we asked two people if they would change their major. Well, both of them could say no, in which case 0 people would change their major. One of them could say they want to change their major, or both of them could say they want to change their major. So now you see why this is a discrete distribution, okay? Because the options here are that 0, 1, or 2 would change their major, okay? Now let's see here. The probability of each of these happening. Now, we can't just figure that out super easily. We have to do a little bit of digging to figure this out. Now, here's what we need to do. So think about this. This is called a tree diagram. This helps out a lot. Okay, so let's say we ask somebody if they would if they started over, they would change their major. Now let's say Y for yes and N for no. So when I first asked the first person can either say yes or no. Okay? Now, what's the probability of somebody saying yes, they would change their major? Well, it's this. Well, 36%. So we'll say 0.36. 0.36. Now, if 36% of college grads say they would change their major, what percent would say they wouldn't change their major? Well, in this chapter we call P is the probability of success. In this case, people saying they would change their major. So 0.36, and we call Q the probability of failure, which is 1 minus P, which is 1 minus 0.36, which of course is what? 0.64. So the probability of somebody saying no, they're happy with their major, is 0.64. Okay, let me fix that. That's a little messy there. Let's fix that. 0.64. Okay. Now let's just work with this top branch of the tree for a moment. Now so we're going to assume the first person said yes, they would change their major. Now what about the second person? Again, the second person has the same exact choice. Either you could say yes, I would change my major, or you could say no, I like my major. And what's the probability? Again, it's 0.36. We're assuming these events are independent because we're picking people at random. So if I pick somebody from Florida, then I pick somebody from California, we're assuming those people don't know each other, and they went to different schools, and they're in no way related. So the events would be independent. So the probability of yes and no stays the same. So no is still 0.36. 0.64. Okay, so what do we have here? We have this event is the event that both people say they would change their major. Yes, yes. Then we have this event where the first person would change their major, but the second person wouldn't. Now let's go down here to the other option. The other option was, what about if the first person said no, they liked their major? Okay, well the second person could say one of two things. The second person could say, no, I like my major again. I wouldn't change. In which case, again, the probability is still 0.64. Or the second person could say, yeah, I would like to change my major. And remember, that probability was 0.36. So this option would be the first person said no and the second person said no. So no, no. And this option down here would be the first person said no, but the second person said yes. Now, since all of these events are independent, to get the probability of yes, yes, we simply multiply 0.36 times 0.36. So we go over here to our calculator, and so we say 0.36 times 0.36. And so the probability of both people saying they would change their major, so we'll say that's the probability of yes and yes, both people change their major, is 0.1296. Since that's only 4 decimal places, we'll leave it how it is, since we usually round probability to 4 places. Now, if we want to look at the probability of yes, then no, it's 0.36 times 0.64. So 0.36 times 0.64. We get 0.2304. Now, I hope you could probably assume that the probability, oh, sorry, I'm out of order here. Next, we have the probability of no, then no. That is, both people like their major and wouldn't change. Well, it's 0.64 times 0.64. Again, we're just multiplying probabilities because those events are independent. And we get 0.4096. And lastly, now here's the easy one. We need to calculate the probability of no, then yes. Well, what do you think? We're multiplying 0.64 times 0.36. We know that multiplication is commutative, and we've already calculated 0.36 times 0.64. That's going to be the exact same thing as 0.64 times 0.36, which is 0.2304. And now we can go back to our distribution that we're trying to fill out. So what's the probability? Again, X says the number of grads who would change their major. So that's yes, would change their major. So what's the probability that nobody said yes? Well, that would be no, no, then no. So the probability we calculated was 4096. The probability of one person changing their major, well, there was 2 different ways somebody could change their major, or could want to change their major. The first person would say yes, the second person would say no, but then the first person could say no and the second person could say yes. So both of this and this satisfied X equal 1. That is, one person wants to change their major. So what you do is simply add those 2 probabilities. So 0.2304 not 0.07, 2304 plus 0.2304, and we get 0.4608. 0.4608. And now the last is the probability that both of them would like to change their majors, which over here in our tree diagram, that's indicated by both people being yes, they would change their major, which we found the probability to be 0.1296, 0.1296. Now, here's the easy way to check yourself to know if you did the calculations right or wrong. We know that in any distribution, the sum of the simple event probabilities has to equal 1. We know that must be true. So let's go over here and add those up. So we could say 0.4096 plus 0.4608 plus 0.1296 better be equal to 1, or we made an error. But we're good. So that checks out. So we know we're good on the distribution because the sum of the simple event probabilities is equal to 1. Okay? So this says here is our discrete distribution. And we can answer questions like what's the probability of, let's see, the probability of x being less than or equal to 1. That is, what's the probability that one or fewer of the two people you ask would say they want to change their major? Well, in discrete distributions, since the events are considered to be independent and all these things work out nicely for us, that's just the probability of 0 plus the probability of 1. Okay? Which is 0.4096 plus 0.4608. So the probability of one or fewer people saying they would want to change their major if they started over again is 0.8704. Okay? You could say, what's the probability that nobody, so x equals 0, or both people, that is x equals 2, would like to change their major. So that's either everybody wanted to change their major, those two people, or nobody wanted to change their major. Well, in that case, that's just the probability of 0 plus the probability of 2. So that's 0.4096 plus 0.1296. We get 0.5392. So 0.53. And there was we answered questions like that. Now again, usually the trouble is translating the English statement into a math symbol statement. But just make sure to read the sentences really carefully. Like when it says, what's the probability of one or fewer, think that means x is less than or equal to 1. If it said 1 or greater, it would be x is greater than or equal to 1. So you just have to be careful with the text. Okay. Now let's see. What about how do you find the mean and the standard deviation? Now we have a couple new formulas here. So let's see what we can do. We have the mean, mu equals. Okay, here's a new formula for it. Oh, and some new notation. In Chapter 5, we also refer to the mean of a discrete distribution as the expected value. E of x, called the expected value. That's if you see that term, expected value, or you see these symbols, just think, oh, they're talking about the mean. Okay, here's the formula. It's the sum of the x times p of x's. So that's not so bad. You take every outcome x, multiply by its respective probability, add up those results. Okay, that's not so bad. Now sigma, the standard deviation, that is the square root, of course, because we know that standard deviation is always the square root of variance. It's the square root of the sum of the x squared times p of x's minus mu squared. Okay, so we have to, over here, we have to square each x term, then multiply by their respective probability, add those up subtract off mu squared, then take the square root, and that's the standard deviation. Okay, so let's scroll down just slightly. Let's see here. That should be enough room. And let's calculate both these things. So in this case, let's go to the mean first. So this says take every x value, multiply by its probability, and then add up the results. So we have 0 times 0.4096 plus 1 times 0.4608 plus 2 times 0.1296. Well, what do you know about 0 times anything? It's just 0. So that first product is 0. 1 times anything is just that anything. So if we want to do the arithmetic here, this simplifies to just saying 0.4608 plus 2 times 0.1296, and so we get 0.72 is the mean. So I ran out of room here, equals 0.72. Okay? So there is the mean. Now what does this tell us? That means if you take these probabilities and these outcomes, the average expected outcome is 0.72. Okay, you know that if you take into account that nobody would like to change their major and one person would like to change their major, those are the most probable cases. Both people want to change their major only has a 0.12 probability. But if you take this into account, that on average 0.72 people would want to change their major. Okay, so not quite whole one person would want to change their major on average. So even though even though we're only dealing with whole numbers as far as x, the mean can be not a whole number because you're working with decimals and stuff. So that's fine. Now let's do the standard deviation. Standard deviation says you have to square each number. So let's see here. I'm gonna go down just a little bit. So go down here, give it a little more room. It's a big square root. Let's see. So we're gonna square the x terms, multiply by their respective probabilities, add them up, then subtract what we already know to be mu, but squared. So we have 0 squared times 0.4096. We know that 0 squared is just 0, so that's easy. Plus 1 squared times 0.4608 plus 2 squared times 0.1296. So that's the sum of the x squareds times p of x's minus mu, which is 0.72 squared. Okay? So let's see what we get for this calculation. So we know that 0 squared is 0, so that first term goes to 0. 1 squared is just 1, so 1 times 4608 is just 0.4608. Plus, 2 squared is 4, so 4 times 0.1296. So that is the sum of the x squareds times p of x's, but then we have to subtract 0.72 squared. And so we get, underneath our square root sign, 0.4608. Okay? And then we do this, take the square root, and we say this, square root. We can say of that previous answer since it's stored for us. And so here's the standard deviation. Let's round it to 4 decimal places. we have 0.6788. So there you go. There is sigma, standard deviation. And of course we have mu, the mean, right there. Okay? So that's how you have to work these problems if you're not this special case that we're going to talk about in just half a second. So that's just a general discrete distribution. Okay? So you have to do things like make a tree diagram. Now here's the thing. If we said we're picking 3 people, this tree diagram would have gotten a lot more complicated. So we really can't ask questions if we pick more than, I guess 3 people probably would be manageable. But if you get to 4 and 5 or even higher, doing this by hand gets really tedious. Is it impossible? No. Is it hard? Really, no. But it's tedious. So it turns out if you have a special case, this thing called a binomial distribution, then the work simplifies a lot. In fact, we could have done this simpler thing that I haven't told you about yet. And so if you're watching this after the lecture, you might have noticed that this is what we call a binomial experiment. Now, what is a binomial experiment? Let's scroll down and talk about it. So here's another example. By the way, it's there's not a whole lot of substantive difference. It says, according to Gallup 2017, 70% of Americans have confidence in small business. Let's randomly select 4 Americans and ask if they are confident in small business. Oh, and let's say further, let X equal the number of respondents that are indeed confident in small businesses, I suppose. Okay? Now, let's talk about what's special about this. In fact, the previous one met these same 4 criteria. I just didn't tell you about it because I wanted to show you how to do it that way. Okay? So let's see. Here are the 4 criteria for being this special thing called a binomial experiment. Binomial experiment. You got 4 requirements. First is there are n identical trials. Now there's a couple things going here. First of all, you have to do the same exact thing, however many times you specify. For instance, here I'm going to ask 4 random Americans whether or not they are confident in small business. So I'm asking them, are you or are you not confident in small business? So I do this exact same thing 4 times. Are you confident? The answer is yes or no. Are you confident? For the second person. To the third person, are you confident? Doing the exact same thing 4 times. So you have to do identical trials. The second thing here says n. What's special about that, you might not understand, but that says there's a finite number of trials. That is, you're not going to have an infinite number of trials. We're having a finite number, a set number. We're doing 5. We're doing 6. We're doing 7. We're doing 2, like in the last example. Okay, a finite number of trials. So that's the first requirement. Second requirement. Okay, there are only 2 possible outcomes per trial. Only 2 possible outcomes per trial. A lot of times we'll call this success versus failure. This doesn't necessarily mean that one thing is good and another thing is bad. Success is what usually we say, that's what we're looking for. For instance, if I ask people whether they have confidence in a small American small business, I'm going to say, if you tell me yes, you do have confidence, that's a success. And if you say no, you don't have confidence in American small business, that's a failure. Now, does that mean a good thing versus a bad thing? Not necessarily. That's just how we talk about the binomial experiment. There are two outcomes. We call them success and failure, even though that you shouldn't think about one being bad and the other one being good. Okay? Now, the third response. Okay? Third response is the two probabilities. That is the probability of success probability of success, we call that P, and the probability of failure, we call that Q, and it's equal to 1 minus P, must remain constant. Now, what I mean by that is P has to stay the same for each trial. Q has to be the same number for each trial. That's not saying P equals Q. It's saying that P and Q, whatever numbers they are, have to be the same when you ask the first person versus the second person versus the third person versus the fourth person, and so on. That P and Q must remain constant. Now, the fourth requirement is that the trials are independent. Okay. Now, what is independent? Remember, we have a definition in Chapter 4. Independent. Okay. Independent means that the one event happening doesn't affect the other. Now, usually the way we verify that is saying we're picking random people or picking random objects. That is, if you pick a random American, picking one and asking them whether they have confidence in small businesses should not affect you picking somebody from the other coast at random and asking them if they have confidence in small business. So they're not related at all. They're picked at random, so that's how we should satisfy number 4. So if these 4 items are satisfied, then we know this is a binomial experiment. Now, here is how we do create the distribution, the chart with the probabilities and outcomes, if we have a binomial experiment. So we go over here, and we say, okay, we have chart. Now, what are the possible outcomes? So here's the outcome column, and here's the probability of those outcomes column. So we're going to ask, let's see, we said 4 people. Now, what are the possibilities? When we ask them, are you confident in American small businesses? The responses can be yes or no. So 0 people could say they're confident of the 4. 1 of the 4 could say they're confident. 2 of the 4 could say they're confident. 3, or all 4 could say they're confident. So these are the only options here. 0, 1, 2, 3, 4. Okay? 4 is the greatest number. 0 is the least number. We're talking about number of responses, so this is discrete data. 0, 1, 2, 3, 4. Now, before, in the previous example, we had to make a t-chart, or excuse me, a tree diagram at this point. But here's the thing. In fact, I'll start to draw you one, and then I'll erase it though. So let me scroll down a little bit actually, so I can get out of the way and not have to worry about erasing too much. So here's what would happen. I have 4 people I'm going to ask. So I would go down here. I would say, ask the first person. That first person could say yes or no. Okay, but then I ask somebody again, and that person could say yes or no. But then I ask again, yes, yes or no. But over here again, here's another possibility, yes or no. So let's say I ask, here's the first question, second question, third question, and here's the fourth person asking all of these. And this is only going to be half of the tree. So yes or no, yes or no. Then we have yes or no. Then we have yes or no. And that's only half of the tree. I still have to do the half of the tree down here. So we have 1, 2, 3, 4, 5, 6, 7, 8 probabilities down there to compute. And then I have yes or no. That is the second question. Then I have yes, or the second person. Then I have yes or no here. And then I have all of these. If I was going to have a tree diagram. Now, look at all the probabilities we'd have to compute. Now, are these hard? No, because we have independent events. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, which, by the way, is 2 to the 4th power. We're talking about 4 people. Each of them has 2 choices. That's 16 probabilities that we'd have to calculate. So you don't really want to have to do that. So I'm going to show you how to use the binomial distribution formula to figure it out. So let's go back up here. Now, here is the binomial distribution formula. It is P of x, that's calculating the probability of x, is n choose x times P to the x power times Q to the n minus x power. Now, here's the thing. Don't let that throw you off. It's not so bad. This is just a number that you get with your calculator. This is just a number that sometimes you can do in your head, other times do in your calculator. And then this is a number that, again, sometimes you can do in your head, but you can do with your calculator as well. So all this is 3 numbers multiplied together is all you have to do. So let's do a couple examples, and then I'll show you how to really use your calculator to make the process go faster. So let's calculate a few of these things. So let's see what we have here. Let's do P of 0 first. That's the probability that 0 people are confident in American small business. Now, we haven't talked about everything here. What is n in this case? Well, n is the number of trials. You're asking 4 people what they think, so there's 4 trials. P, that's the probability of success, well, 0.7. Q, that's 1 minus P. It's the probability of somebody, in this case, saying they don't have confidence in American small business is 0.3. Okay? So 0.7 and 0.3. 0.7, of course, is the probability of success, what we call success in this case, because if you're confident, we're going to say that's success. And let's see what we have here. So let's plug into our formula. N is 4 for all of these examples. So it's 4, choose, okay, x is 0. So 4 choose 0 times P to the 0 power. Oh, we need to plug in what P is. P is 0.7. So 0.7 to the 0 power. So this times Q, which is 0.3 to the n minus 0 power. So 4 minus 0 power is 4. Now, these are just 1 number, 2 number, 3 numbers we need to figure out what they are and multiply. Now, if you have done your Chapter 4 homework, you've probably noticed there's something special about any time you have choose 0. 4 choose 0, 5 choose 0, any number choose 0. Let's see real fast. So you go over here to your calculator. 4, go to the math menu, scroll over to the probability menu, go down to NCR, and 4 choose 0, and what do you get? 1. Any whole number, choose 0, is 1. Okay? So that first number looks like it would be difficult, but it's just 1. Now, what's a non-zero number raised to the 0 power? Well, from your algebra, you hopefully remember that's also 1. So all we really have to do here is raise 3 to the 4th power, and we're done. Oh, not 3, 0.3 rather. 0.3 raised to the 4th power, and we get 0.0081. So that tells me that the probability of nobody being confident in small business is pretty small. It's 0.0081. Because 1 times 1 times 0.0081 is just, of course, 0.0081. Now, let's try the probability of, let's see here, the probability of x equals 1. So the same calculation, except instead of zeros, you have ones. So that's 4 choose 1 times 0.7 raised to the 1st power times 0.3 to the 4 minus 1 power. Again, that's just 3 numbers. Now, this is also kind of a special case. 4 choose 1 turns out to be 4. Watch this. 4, math menu, scroll over, choose 1 is 4. Any whole number, choose 1 is always that same whole number back. So this first number is 4. The second number, 0.7 raised to the 1st power, is 0.7. Now, this is 0.3 raised to the 4 minus 1, so 3rd power. I'm not sure what that is. 0.3 raised to the 3rd power. Oh, I should have known that. It's 3 times 3 times 3. Move the decimal place. Yeah, I wasn't thinking about that. 0.027. So if I multiply those 3 numbers, let's see, 0.027 times 0.7 times 4, and we get 0.0756. So 0.0756. And now we can just repeat this process over and over again to fill out the chart. Now, let me show you how to make it go faster. Actually, let me do one more. We've only done 2. Let's do a 3rd one, then I'll show you how to go really fast. Okay, let's see. One more before we skip on. Let's do P of 2. That is, find the probability of x equals 2. So that's going to be 4 choose 2 times 0.7 to the 2nd power times 0.3 to the 4 minus 2 power, which is also the 2nd power. Now let's see. 4 choose 2. Go over here. 4 choose 2. That's 6. You could do that by hand if you wanted to. We talked about the formula in Chapter 4. I wouldn't really necessarily worry about it. Let's see. 0.7 squared. Okay, 0.7 times 0.7. 7 times 7 is 49, so 0.7 times 0.7 is 0.49. And then let's see, we have 0.3. Now that's that's a little messy there. That's to the 4 minus 2 power. So 4 minus 2. So that's 0.3 squared. Now, of course, 0.3 times 0.3 is like 3 times 3, 9, except we're going to move the decimal place. 0.3 times 0.3 is 0.09. Okay, so multiply those 3 numbers together. We have 0.09 times 0.49 times times 6 times 6, and we get 0.2646. Okay, so we go over here, 0.2646. Now let's say I want to do the really fast way for 3 and 4. I'll show you two really fast ways to find the probability of 3 and the probability of 4. First of all, I'll use the calculator. We can use the calculator to find, let's go here and just write it out. We can use the calculator to find P of 3. And here's how you do it. You go to the calculator, you go to, let's see, you need to go to the distribution menu right there. So we hit second vars. That takes us to the distribution menu. Then we scroll down till we get to binomial PDF. Okay, click binomial PDF. Now, if you have a newer calculator, yours might look slightly different. If you have one like this, which a lot of people have these A3 pluses, here's what you have to do. And if you have a new one, you'll just have a nicer menu. You have to tell the calculator the same thing. You need to tell your calculator how many trials you're doing, what's the probability of success, and then what probability are you trying to calculate in that order. So we have to do, let's see, we have N, so 4 trials, comma, the probability of success we said was 0.7, that's P, so 0.7, comma, what probability are we trying to calculate? That is x equals what? We're trying to calculate the probability of x equals 3, close the parentheses, and that's all you have to do. So that probability, again, you have to do binomial, binom PDF, and you have to do NPX. So in this case, N equals 4, P equals 0.7, and X, we were trying to calculate the probability of 3. And it turns out that probability is 0.4116. Now, what's the other way to easily get the probabilities? Not in all cases, but in some cases. I'll show you how to do that. It's the chart in the back of the book. Now, let's take a look at the chart in the back of the book. Minimize this real fast. All right, this is the binomial distribution chart in the back of the book. Okay, it's in Appendix B, I believe. Here's what it does. You first need to find the n you're looking for. Now, we were looking for n equals 4, so we're going to look at this group of data down here. But then you also have to pay attention to the columns. Now, here's the thing. This chart only gives us probabilities if P is 0.5 or 0.95 or an increment of 10. Now remember, what was ours? We had a probability of P equals 0.7. So this chart works for us. But if we had P equals 0.75, we couldn't use the chart. We would have to use the formula or a calculator if we didn't want to do it by hand. But if P is 0.05, or 0.95, or an increment of 10, we can simply use the chart to easily find all the probabilities we need. So let's scroll down a little bit. All right, so let's see here. We have n equals 4. Essentially what each of these columns are is this column is the probability distribution when P equals 0.5. So this is the probability of 0. This is the probability of 1, probability of 2, 3, and 4 if the P probability of success was 0.5. So now we're dealing with the probability of success is 0.7. So notice what we have here. This number should look familiar. Always error messages. All right, we're almost done, so it's fine. All right, so we have the probability, okay, the probability of when P is 0.7 and the probability of 0 successes is 0.081. That should look familiar, exactly what we found it to be. Going back over here, the probability of x equals 1, again, we're looking at only this column, and we're looking down here because this is all the instances where n equals 4. If n equaled 3, we would have to be looking, up here in the 3 block. But we're looking in the 4 block, and we have the probability of x equals 1 is 0.0756, which is exactly what we found it to be. What about the probability of 2? 0.2646, exactly what we found it to be. What about the probability of 3? 0.4116, again, exactly what we found it to be. And what's the missing piece? This last one right here, 0.2401. So that's the last one, the probability of 4 successes out of 4 is the last one, 0.2401. So 0.2401 was the last one. Now, let's double check ourselves. Of course, the chart just told us we were correct. But remember, you always want to double check yourself by looking at the sum of the probabilities. Add all those up and see if you get 1. If you get 1, you're good. If you don't get 1, then you made a mistake somewhere. So let's see. 0.0081 plus 0.0756 plus 0.2646 plus 0.4116 plus 0.2401, and hopefully we're good. Yes, we did get 1. So we're good there. Okay, if that had not equaled 1, we would have had a problem somewhere. Okay, so now that we've gotten that, let's just do the mean and the standard deviation, and then we'll call it a day. Of course, we could ask questions. Maybe I'll ask a question or two regarding this. Yeah, I'll ask a question or two regarding this. Now, let's see. Remember, I told you there was going to be some easier formulas. Here they are. If you are in a binomial distribution, mu equals NP. Super easy. Sigma, the standard deviation, equals the square root of NPQ. So NP here, what's NP? Well, N is 4. P is 0.7. So what do you think N times P is? Well, it's just 0.7 times 4. So 4 times 0.7 should be 2.8, I believe. Right? Because 4 times 0.7 equals 2.8. Now, what about the square root of N times P times Q? Well, N times P times Q, well, N is 4, P is 0.7, and Q is 0.3. So there's N times P times Q. Take the square root, and we get, oh, let's round this to 4 decimal places. So 0.919165. So the nice thing about the binomial distribution is that the standard deviation and mean are very, very easy to come by. Now, don't mistakenly use these formulas if you're not in the binomial distribution, because these formulas will give you an answer, I suppose, but will be incorrect if you use these in error. Now, the thing is, you could always use going back up here, you could use this formula and get the exact same answer for mean, or this formula. So the general discrete data formula for mean and standard deviation work whether you're in the binomial distribution or not. However, the binomial distribution formulas do not work if you're not specifically in a binomial distribution. Okay, so you can use the regular discrete distribution formulas if you're in a binomial distribution, but not vice versa. Okay, so just keep that in mind. Okay, let's see. Last couple things. Let's ask a question or two. Let's scroll down. Just give us a little more room so we can still see our distribution. Let's find the probability, because this is stuff like you would see on a homework quiz or test. Find the probability that, let's say, at most 3 people are confident in small business. At most 3. So be careful with the at most, at least, more than, less than. Be careful of those. So what's this asking us to do? This is asking us to find the probability at most 3. So that tells me x is less than or equal to 3. At most 3. So we need to add up probability of 0, everything less than 3, or equal to 3. So probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3 is what we're looking for there. So let's see. The nice thing about, again, these discrete distributions is that all you have to do is add these respective probabilities now. So the probability of 0 is 0.0081 plus the probability of 1 is 0.0756 plus the probability of 2 we said was 0.2646 plus the probability of 3 is 0.4116. Okay, so 0.7599. Now, what do you notice that is also equal to? That is equal to 1 minus the probability of 4. Because x equals 4 is the complement of x is less than or equal to 3. Remember what the complement means. If this is an event x is less than 3 is one event, everything in the sample space that's not in that event is the complement. Well, the only thing not included in x is less than or equal to -3 is x equals 4. So x equals 4 is the complement, and we know that the probability of 1 minus the complement, the probability of, let me back up, 1 minus the probability of the complement is equal to the probability of the original event. So notice 1 minus the probability of 4 is 1 minus 0.241, which is that number exactly. Okay? So let's do one more. Let's say the probability, let's say that at least 3 people are confident in small business, American small business, but I'll abbreviate, in small business. Okay, at least 3. Okay, well that's just 3 or 4, so the probability of 3 plus the probability of 4, which is, let's see, 0.4116 plus 0.2401. Oh, I messed up. Let's go back over here. It's 4, let's see, insert 4116. 4116, yeah. So the probability there is 0.6517. So, again, let's just wrap it up now since we asked a few questions. We're right at an hour now. So we first talked about the just general discrete distributions. In general discrete distributions, you have to figure out the probability probably using a tree diagram like this. Now it turns out this question actually could be, we could have done a binomial here. This is a binomial experiment. Okay, I just didn't tell you about it because I wanted to do an example both ways. Okay, so we did a tree diagram, we figured out the probabilities, and the thing was, if you don't know it's a binomial experiment, the formulas for mean and standard deviation are a little more difficult. However, if you can verify that the experiment you're talking about is binomial, then you can use the binomial probability formula. You can use a calculator to do a lot of the work for you, and if the p-value is an increment of 10 or 0.5, 0.05, or 0.95, sorry, 0.05, 0.95, or an increment of 10, then you can use the chart in the back of the book. So even if you don't have a calculator to speed the process up, if you have, like in this case, 0.7, the chart will give you the entire probability you need. All the probability distribution values you need, the chart in the back of our textbook will give that to us. Now, if it's, say that was a 0.75, we couldn't have used the chart, and that's fine. We'll have to either do it by hand or use the calculator to help us out. Okay? If you have any more questions, feel free to ask. Always available via Blackboard to answer your questions. Talk to you soon.